Hi guys, welcome to another video. We're going to be covering 1.3 rates of change. And this topic mainly helps us figure out what type of function we have given a table. And so we'll see here with some few examples as we kind of go along. So let's kind of start off with reading the statement here. For any linear function, the average rate of change over any length input value interval is constant. We often think of this as the slope of the line. Slope of the line. And now we're given a table. Specifically, this table gives selected values of the function f of x. Explain why f of x is not a linear function. And I would say there's two ways to approach this problem. A very generic way that I think is very common is that I would try to graph this and then see whether or not it looks linear or not. Right? And I'm just going to do a really quick sketch of the points. Right? So I might label my axes or number them all the way to 8 here for the x-axis, and then all the way up for 13 for the y-axis. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? A little off, it's okay. And so let's start graphing some points. I have 1 comma 4, 2 comma 7, 4 comma 10. So far it kind of looks linear, but you can kind of notice my points are kind of off. Even though maybe my spacing might be kind of off too. That might be the reason why. But as you kind of see this last point though, 8 comma 13, this is definitely not linear, right? If I was to connect my points, and already is not going to be linear at all. So that's one way to kind of approach it. The other way would be to observe the table itself and how the values change. So let's take a look. Let's say for some reason you kind of want to observe the average rate of change or perhaps a slope between the points or the intervals, right? I notice here that I'm changing from 1 to 2, that's a difference of 1. From 4 to 7, there's a difference of 3. So inherently between those 2 points, I can kind of see that I'm rising 3, right, and running 1. So a slope of 3 technically. Hopefully that slope stays consistent if I want to be considered linear. As we compare the next set of intervals, right, from 2 to 4, I have plus 2 and plus 3 again. This time we have 3 over 2, right? And that's not the same slope as the one we had a moment ago. So that alone contradicts that this cannot be a linear function. And so those are two good ways to approach it, but we'll see a better way here pretty soon, right? And here's number 2. I'm going to read this out, and while I read it out, perhaps you can go ahead and just start filling in what we have so far, or what I have so far. Okay? It says consider the quadratic function f of x equals x squared. Complete the table's values for g of x over the consecutive equal length input value intervals below. Then complete the table for the average rate of change of g of x for each consecutive interval of equal length input values. Okay, perfect. So as far as a regular table on this side here for the function, um, I'm not sure why it says g of x this time, f of x, right? That's what it should be, right? Negative 3, wait, yeah, right. Negative 3 squared is 9. I don't know why I got caught up on that, right? So if you were to plug in all these x values into here, these are the outputs you would have from the y column. Now let's go and start looking at this table where we're kind of calculating our average rate of changes for these intervals that are provided to us. You can see I did the work for the first one. That way you can kind of double check that, hey, this is still a skill that we have already done and we'll continue to practice, right? But if I was to do it for the rest of them, these are the numbers I would get. I think you can try to do some on your own if you'd like for the work, but I'm not going to. So let's see what's asked of us next. Now it's saying, what do you notice about the average rate of change of g of x over consecutive equal length intervals? Well, as we observe the average rate of change, right, these are all the consecutive lengths that are exactly the same, right? From negative 3 to negative 1, I mean, that's a total of a difference of 2. From negative 1 to 1, that's a difference of 2 as well. So that's what they mean by that, consecutive interval changes, right? They're the same amount each time. And so we notice that the average rate of change is currently increasing. Or, well, initially it decreases by 2, and then increases by 4, and then increases by 8, right? And so based on that information, I can say, well, it's no way that can this thing be linear, right? Uh, we know for a fact that if the average rate of change were consistent all the way through, then we'll claim that it's linear. Hold on, my cat is going crazy. I'm gonna pause the video. All right, I'm back. Sorry about that awkward pause, but yeah. So essentially, we figure out that hey, the average rates of change are in general increasing, right? Are in general are general are in general increasing. How do I say the average rate of change is increasing? Right, that sounds better, right? Thus, we can claim that this function is nonlinear. And that should have already been true right off the bat. Let's think about what type of function we were graphing in the first place. They gave it to us, right? We had f of equals x squared, which, if you recall, this is a quadratic function, right? So there's no way this could have been linear anyways, right? So really what we're doing is just evaluating the behavior that makes this claim true. That might be a useful fact later. All right, let's move on. Now let's talk about regression models. So I'm gonna read through this, and you can kind of fill in what I have filled in already, right? It says from given data, we want to analyze the change in x and y's values to find a pattern that represents the data. The data can be given in multiple forms depending on the scenario. Could possibly be a table or ordered pairs. And so regression models only work with addition and multiplication. Regression models do not work with subtraction or division. However, technically, the loophole for subtraction is saying we add a negative number, which is the same thing as subtracting, right? And the loophole for division is multiplying by a fraction, which is essentially the same as division, right? So those are our loopholes to do that. And then we have this table as far as how to figure out what type of function we have, depending on the pattern that we see for x and for y, given a table or ordered pairs. Now I said a lot just now. If you want to go back in the video and re-listen, you can. I would suggest that, hey, just kind of stick around. Go ahead and let's try out a few problems here that are about to come up and see how we use this table and how we can recognize um, the patterns for x and y to determine what type of function type we have. Okay? And so as we go along, knowing how to calculate regressions as well will be a good idea, as I will be writing the functions down. However, I don't have access to a Casio to show you what I'm pressing. I'm hoping that you can kind of follow along with these steps once I prompt you to do so. Okay, so if you have a Casio, use the left column. That'll help you do that part. You have a TI, do the right hand side, and that'll help you calculate regressions. All right. Now that we have that said, let's move on to actual problems, and we'll use that previous table to help us, right? And so you can scroll back up to recall it. And so what we're going to do first is recognize the function pattern. And the way we do that is by looking at the differences, or perhaps how it's multiplied sometimes. But I always like to look at differences first. So what I do is compare one interval after the other and see how much is changing, right? In the first one, from -2 to -1, I'm adding 1, so on and so forth, right? That should be the pattern for x. So it seems like we're adding. And since it's already the same values as well, I don't have to keep going, right? I don't have to look at the second difference of these. These are already good. Now I'm going to look at the first difference for the y values. And we can notice immediately as well, they kind of follow the same pattern, right? We're already adding 1 just each time. And so this is a pretty quick indicator, right? This is add, which determines my function type to be linear, right? So essentially, I'm just using the ideas from this table here, right? Add, right? If I have the same pattern, add for the x and y, I can claim that the function type is linear. So to recall, the old thing that we did was, well, we compare the average rate of change each time. And you can notice that they're the same each time, right? 1 over 1. So of course it has to be linear. But it might be a good idea that we're kind of referring to this table here for determining that. And so at this point, we just need to be able to find the function rule. So you can calculate regressions right now by using your calculator, putting the table information into your calculator, and calculating the proper regression. And then you can kind of pause here and then check if you got the right equation for it, right? But this one you might be able to tell just by the graph though. It should be y is equals to x plus 4. Right? The reason why I say you can just observe the table is that, well, the slope is definitely 1, right? Every single time we're rising and running 1 based on the differences we found. And then I noticed this point that they gave us here, which was very nice. That's the y-intercept. And so just knowing that, I already knew that the function should be this. If not, you could have just plugged this into your calculator, calculate the regression, and you would also get the same answer. All right, now let's move on to number 2. Again, we're going to find the function pattern. So let's calculate the first difference and see if the pattern already ends there. So here's me calculating the first difference for the x values. And it seems like we're adding 1 each time. Nothing out of the ordinary there. I don't have to keep going. Now let's check here. And again, I like to check how much they add. And in this case, they're adding 2 each time the first time here. And then plus 6. And then plus, what is that? 9, so 18. And this one is, I believe is 54. Right, so it doesn't seem like we have a pattern quite yet with the first difference. And so I might do the second difference and see if we get a pattern there. So from 2 to 6 here, I'm calculating the difference between those two numbers. I see a difference of 4. I'm adding 4. Then I'm adding 6 to 18. I'm adding a total of, well, I can't do that math for some reason, 12. And then from 18 to 54, I definitely can't do that in my head. I'm going to cheat here and use my phone. 54 minus 18. So I'm adding 36 to get there. But again, the second difference here, right? I don't have anything that's different either, right? Or sorry, the same, right? So I calculate the first difference. I found no pattern. I found the second difference. I found no pattern. And so I'll try a third time, right? And you kind of notice again that there's still not going to be a pattern. I'm like, it's still nothing, right? Still nothing. And even finally, after this point of doing it so many times, there's still no pattern until I reach the end here, where I'm just adding, what is that, difference of 16 here, plus 16. So this is not exactly very helpful, looking at whether or not it adds. Now, you might have been yelling at me the whole entire time as I went through that, and you're like, well, Mr. Bowie, like, I already noticed the y values are already multiplied by 3, and I'd be very proud of you, okay? And you're entirely correct, right? They're not adding. This one has a clear pattern where each time the y values are being multiplied by 3 every single time. And notice that just doing that, all the values are the same, so we have found our pattern. So we know that it should be add and then multiply. And then in case you forgot what that means, I'll just refer back up to the table where we filled it out already. Add, multiply, that means I have a function type that's exponential. And so I will claim now that this function type is exponential. And then I would input these x and y values into the calculator and then calculate a regression. But if not, you can just simply check what answer I write down here and you'll be solid. It should be y equals 9 times 3 to the power of x. Now this was also possible to see just by looking at the table if you're familiar with the exponential functions and what they look like, right? Remember it's y equals ab to the power of x, right? And you can kind of see it here. If not, just calculate regressions. All right, let's do number 3 now. Again, same thing. Let's find the first differences. And it seems like the x values I already have a pattern on the first difference. I'm just adding 1 each time. And then I'll calculate the differences for the y values. So let's do the first difference here. That's plus 6, then plus 8, then plus 10, then plus 12. So no pattern quite yet on the first difference, but I think as we calculate the second difference, we will have one. So from 6 to 8, that's plus 2, 8 to 10, plus 2, and 10 to 12, also plus 2. So on the second difference, we were able to find a pattern. So I can see that this is add and second difference, right? We claim that we had a pattern on the second difference. That's what you're kind of looking at in terms of referring to the table. And so if I scroll back up, I think add and second difference is considered to be a quadratic. Okay. Eventually, as you use this table a lot, you start to remember, right? For me, I kind of just think about it not really for the table, but I just think about first differences. If that stops there for both x and y, automatically linear. If it's first difference for the x column and then second difference, then I know it's quadratic. And then if it's still first difference, add, and then it becomes third difference, I know it to be exponential. But again, that's just how I memorize it. Do what you need to do to memorize that table. And then the function rule, right? There is, I would say complicated. There's a long way to actually mathematically find the equation without regression. If you're curious about that, I can show you that in class at some point. If not, just put this into the calculator, calculate the regression, and you should be good, right? And so I'm going to act as if you calculate the regression. You should have end up getting an equation, y equals x squared plus 5x minus 6. And somewhat partially, you could just look at this table and figure out the equation, but not entirely. You would really need to do a whole lot more math. All right, let's do one more. Number 4 here. And again, I'm going to calculate the difference for the x values. And this one's really straightforward. It's plus 1 all the way through. So majority of them should be that way. And then the second time around, let's see, 70 to 34. I think that's minus 36. 34 to 16, I believe is, what is that? Minus 18. And then 16 to 10 is minus 6. And then 10 to 10 is 0. And now I'm going to calculate the second difference since I don't have a pattern yet. So negative 36 to negative 18, that's a, well, plus 18. Sorry. Negative 18 to negative 6, that's adding, what is that, 12? And then the last one, I have to add 6. And so, again, still no pattern on the second difference. Hopefully we have one on the third difference, which we do, minus 6 and minus 6. So I have a function pattern of add, and then I see that we have third difference. And if I recall correctly, if I scroll back up to my table, an add and third difference should be representing a cubic function. And I'm right. All right, so I know it's going to be cubic. And as far as what equation this is, again, calculate the regression. Sorry, you should get y is equals to x cubed plus x plus 10. I'm going to pause here. I need to do like a coughing fit. Give me a second. All right, I'm back. I had a coughing fit, drink some water. Hopefully I can finish the video. All right, now we're asked to do the same thing, but now give it ordered pairs. And if looking at ordered pairs is too much for you, like it is for me, I can't really think that straight about it. Maybe some of you guys can, but I might just rewrite it as a table to observe it the same way we just did a moment ago, right? That's probably something I'm comfortable with doing. You could do that as well. If not, you're like so good at calculating first difference and second difference like this, do it. It just looks messy personally. All right. So I'm going to start writing them down. 0, 8, 1, 3, 2, negative 4, and then 3, negative 13. All right. And so I can already tell on the x column here that the first differences are already adding plus 1. So I'm not going to write it again and again. And then I'll kind of focus up on the y column, right? That's going to be minus 5, then minus 7, and then minus, what is that, 9? And then we have a, what is that, third difference, sorry, second difference of minus 2 each time. So I have add and then second difference as my pattern. And so the function type here, based on the table we had above from earlier, add and second difference is quadratic. I might just start saying this is first difference, to be honest, because that's when they're all the same. But anyways. And then the function rule, if you were to put this set of, what is it, the set of points into your calculator and then calculate the regression, you should end up getting y equals negative x squared minus 4x minus 8. And it seems like we're repeating the same process one more time. I kind of overdrew too much from the other one, right? With the new set of ordered pairs. So again, I'll make another table 0, 4, 1, 2, 2, 10, 3, 34. Oh Lord, there's a lot. 480, and then 5 and 154. I can already tell that this is definitely not going to be linear, and more than likely it's probably not going to be quadratic. But again, we should always double check, right? Let's just see if my assumption is true. So for sure, x column, I'm adding 1 each time, so I know that one's just simply add. Already found the pattern. And then here I'll check, right? That's minus 2, then plus 8, plus 24, plus, what is that? 46, and then, oh, what is that? I don't know. 20 plus 54, 74, right? So no pattern quite yet. I even tried to check originally too if they were multiplying. They're definitely not. So I'll calculate the second difference now. That's plus 10, plus 16, plus, what is that? 22. And then last one is plus mental math. Help me out. That should be at least 30? No, 28, I think, right? Plus 28. I'm going to double check because I feel like my mental math could be horribly wrong, and I don't want to continue to give you a wrong number here. So from 46 to 74, let's subtract those. Yeah, it is 28. So mental math is pretty good. I'm running out of space though. I haven't found my pattern yet. I'm sorry if it's not neat, but hopefully you can read it. Now I'm going to calculate, what is this, the third difference? So it's plus 6, ooh, plus 6, and then plus 6. So we did find a pattern. Nice, on the third difference. And then the function type here would have to be cubic. And the function rule, so basically the equation that represents this table or this ordered pair is y equals x cubed plus 2x squared minus 5x plus 4. Okay, so there's that. Now let's move on to something a little bit different. Not really different, but we're just giving a table again. And so it is possible to do this slightly different. I'm not sure why we'd want to. You could use the average rate of change here to determine uh, how to do these, but I'm going to stick with using what I've known so far. Okay, so let's observe. Let's see. That's plus 1, plus 2, and then plus 3. And then this one is plus 1, plus 3, and then plus 5. And so with that alone, I can already tell that this is going to be neither. Okay? So the reason why I say it's neither is that I didn't find a pattern on the bat for x values. Typically, the x values should just have a difference of 1 right off the bat, right? Add 1 each time. And so that alone tells me this is not linear, right? Since every single average rate of change here is different, right? 1 over 1, 3 over 2, then 5 over 3. All of those slopes are different, so ain't no way it's linear. And then if I try to think about it being quadratic, it doesn't fall under our pattern like we mentioned a moment ago, right? This should all be plus 1. And then I should be able to find a second difference here, which I think I do technically. But the first part is not true, right? It's not adding the same amount each time. So thus, it can also be quadratic, even though you may have thought it was based on this. But the first part wasn't true, right? So with that being said, it's not linear. It's not quadratic. Thus, it must be neither. All right, now let's do part B and see what happens here. All right, so as I observe the differences, I have plus 3, plus 1, plus 3, and then plus 5. And then this is plus 1, plus 3, and plus 5. And so as we kind of just observe the average rate of change, right, not even about the second differences at all, no pattern here, I'm just looking at the slopes here, they're all the same, which means this should be a linear function. So we're kind of mixing both rules now, either using that table to be able to figure out whether or not it is quadratic, linear, or whatever. Or, hold on, my cat is eating something. Be right back. Alright, sorry, my cat was eating stuff. He's now in cat jail with me. Hopefully he doesn't get in trouble again and I can finish this video. You gotta stay. It's okay. Alright, so let's see. On this last table, I can already see that the first difference amongst the x values is going to be plus 1 each time. And then, okay, my cat's going to go. Okay. And then the y values, it seems like I'm adding 1, then 3, and then 5. But then I can already see that the second differences, though, are going to be plus 2 each time. And so I'm using the table at this point, those rules, right? I'm add and second difference, which means this should be quadratic. I don't know why I'm being so lazy to write neatly, but all right, so my mic cut off on the other video at some point, so I'm just gonna continue off where that stopped, which should be right about here is where that cut kind of happened. So again, all I did was calculate the second difference. I got plus 1, plus 3, and then plus 5, and then I got plus 2, plus 2. So I finally found the pattern at the second difference, which lets me claim that this function is quadratic. And then if I kind of continue here, these are just simply some things that we've already covered before about what it means to be concave up and what it means to be concave down, where if the average rate of change is increasing and you observe that, then it's considered to be concave up. If it's decreasing, as indicated here, then it's concave down. And so this next part here, technically, you should be doing the average rate of change yourself, and we would go through it together. However, I think we've covered it so many times that I don't need to in this video. If you really want to see it, you can look at the previous video on how to do that. I think it's actually in the first video. But simply just look. That I already wrote the average rate of change for you for every single interval. So this is not second difference or first difference or anything, right? This is average rate of change. So look at the first table from 1 to 1.1, average rate of change is negative 30, and you can see the rest of them as well, right? And so you can see that it's increasing in average rate of change, so we can claim that this one here is going to be concave up based on that information alone. And so if we look at the second table, I've already calculated the average rate of change for you. It's all the same. So it's neither increasing or decreasing, which lets me believe that there is no concavity. There is neither concave up or concave down. And then the last one, here's the slopes, or not, yeah, the slopes for this one as well, where you see that it's decreasing in each interval. And so I can claim that this has to be concave down. And so with that being said, that is the end of the video. I hope you guys have a good day, and I'll see you guys on the next one at some point. Bye. Have a good day.